Welcome everyone to Fieldstone King's College School and to Physics Grade 11. This is the very first lesson and we're starting with Unit 1, Kinematics. And kinematics is all about motion. So we're going to start the very first lesson talking about distance, position, and displacement. To start off, what is kinematics? Well, kinematics is the study of motion. And the first type of motion we're talking about is distance. Distance, we use the symbol d for this, and it is the total length of the path taken by an object. So the total length of an object's path. Okay, and we use units of m for meters. Great, so let's take a look at an example of distance. We have a picture here with home, school, and the library. And it says, in the figure above, how far will you have traveled if you walk directly from your home to your school? Well, we can see that home to school, here, we have a distance of 500 meters. It tells us that right in the picture, so we can write that there. D equals 500 meters. Great. And B, it says, what if you walk from your school to the library and then walk home? So we go school to library and then all the way back home. Well, for that, we're going to need to figure out first how far it is from the school to the library. We're told that this total distance is 1,200 meters. That's from home to the library. And this piece is 500. So this is going to be 1,200 minus 500, which is 700 meters. So that tells us we go 700 meters. So distance is 700 plus another 1,200 all the way home. So that equals 1,900 meters. That's how we work with distance. And hopefully that seems a bit familiar to you. Now, a new concept are the concepts of position and displacement. Before we can actually talk about what those are, I need to make a distinction for you between scalars and vectors. A scalar is a measurement with only magnitude. And magnitude is sort of another word for size. So distance, which we looked at above, distance is a scalar measure. It only has a magnitude. And by only it has a magnitude, I mean it doesn't have a direction. And that's the difference between that and vectors. Vector has magnitude and direction. So a vector has a magnitude and a direction, and it is represented by an arrow. And for instance, if arrow was my variable, I would put an arrow like that over it to mean that it is a vector. Okay. So now that we have those terms, let's talk about position and displacement. Position is sort of like distance, but it's a vector. Position, the symbol is d with an arrow over it, and this is the distance and direction of an object from a reference point. And so position is a vector. Now, by reference point, I mean just some location that we choose to be 0. So when we talk about an object's position, we always need to say it's at this position relative to home or relative to the school. There's some reference point. Okay, so that's position. And now our next term is displacement. Displacement has this symbol, delta D, with an arrow. And we'll talk in a second what the delta means. But displacement is the change in position. Okay, so when something changes in position, that's called displacement. So if I'm moving from one position to another, we can say that there was some displacement. And displacement is a lot like distance, except with a direction. So displacement is equal to our final position minus our initial position. And I've used F and I, final and initial, so the end position minus the starting position. And another way of writing that is d2 minus d1. And it is a vector. Just like position. Position also was a vector. Okay, and the last term here, this delta. In displacement we had delta D. Delta is a term that you'll see a lot in this class. And delta just means the change in a value. Just like we had delta D was the change in position, we could have delta of anything else. For instance, delta x is equal to the final value of x minus the initial value of x. And delta, it's this triangle, it's a Greek character. We use a lot of Greek characters in physics. Alright, great. So moving on to the next page here, we have the same picture with home, school, and the library. We've added on the mall, and now we're going to do a bit of position and displacement. So in the figure above, what is the position of the school with home as a reference point? The position of the school. Well, we can say position is this symbol here. And we know that the school is 500 meters away, so it's 500 meters. And we need to say the direction. So in this case, I'm going to say it's 500 meters east of home. And that's because we're saying here we have west and east. So we're saying that the school is east of home. And you see how I wrote the east. I put square brackets and then put the letter E. Now the position of the school with the library as a reference point. Now we're looking relative to this. Well, now the school is, we said, 700 meters from there to there. So the school is 700 meters west of the library. D equals 700 meters west. All right. Now imagine that you walk from home to school in a straight line route. What is your displacement? Using home as a reference point. Okay, so remember we have our definition here. Delta D, that's displacement, is equal to our final position minus our initial position. And that's how we're going to use this. We're just going to use that formula. Now you could probably tell me the displacement without doing this math. You could probably look at the picture and say, well, I think I know the answer. But let's do it this way. So we have our final position. Our final position is at the school, and that's relative to home. So the position of the school is 500 meters east of home. So we have 500 meters east minus our initial position. We start at home. Home is our reference point, so we're nowhere. We're at 0 meters, and we're not east or west, so we don't put any direction in that case. So there's our displacement, 500 minus 0. Of course, we end up with 500 meters east. Okay, so that's good. Now, the next problem, we're going to look at the same idea, but different values. What is your displacement if you walk from your school to the library? Again, displacement equals df minus di. And now we take the position of our library. That's our final position. And we know that that's 1,200 meters from home. Remember, we're using home as the reference point. 1,200 meters. And we're 1,200 meters east of home. That's our final location. And our initial was at the school. Our school is 500 meters east. Good. Those are our two values. 1,200 minus 500, we get 700 meters east. That's our displacement. Now, the last one says, one night after working at the library, you decide to go to the mall. What is your total displacement when walking from the library to the mall? Again, displacement equals df minus di. And for the first few problems, we really probably didn't need to do this. We could have looked at the picture and answered it. That's maybe true for this one too, but you'll find that if you use this every time, when problems get harder, they end up being the same to solve and you don't have any troubles. So using this formula every time will always get you the right answer. So our final position, we're ending at the mall. That's 1,000 meters west of home. We're starting at the library. That's 1,200 meters east of home. So final was 1,000 meters west minus 1,200 meters east. Okay, now notice I have west and east, and I can't just subtract those straight away. I can't say 1,000 minus 1,200 is negative 200 and go from there. I need to make them have the same direction first. So 1,000 meters west, okay, we can work with that. 1,200 meters east, well, I'm going to write this again, 1,000 meters west. I have minus 1,200 meters east. If I change the sign, then this is my new statement, because I can say 1,200 meters east is equal to negative 1,200 meters west. If we change the direction to the opposite direction, we can just flip the sign. So here we have 1,000 plus 1,200. That means I'm going 2,200 meters west. Okay, and that checks out. If we look at the picture again, we're going 1,200 here plus another 1,000. That makes sense. But it's important that you understand what we're doing here with the numbers, how we're changing the sign here. This is very important. Okay? Good. Now, if you do have any questions, please ask me. I'm here to help. The next question here is, a dog is practicing for her agility competition, and she leaves her trainer and runs 80 meters due west to pick up a ball. She then carries the ball 27 meters due east and drops it into a bucket. What is the dog's total displacement? Okay, so it's always a good idea to draw a picture then when you're looking at this sort of problem to figure out what's going on. Here's the trainer. The dog runs 80 meters this way and then runs 27 meters this way. That's 27 meters. Okay, and so we can do this. We have delta D. Well, in this case, sort of we have two displacements. So I'm going to say the total displacement is equal to the first displacement plus the second displacement. And this is how we're going to solve this one, because we can just add these displacements. So the first displacement was 80 meters west, and then we've got 27 meters east. Again, we want to fix the signs here, so we've got 80 meters west, and this becomes a negative, negative, oops, okay, 80 meters west minus 27 meters west. And that gives us a total of 53 meters west. And there's our final answer. Great. Okay, let's take a look at the final page. And this one says vector scale diagrams. So that's sort of what I just did in that last question. I didn't really use a scale, but I did make a little diagram to help me. So a vector scale diagram is where we draw vectors and vectors, when we draw them as arrows with a certain scale. For instance, one centimeter to 1 kilometer. So when I'm making a scale diagram, my goal is to draw a diagram that actually has the right proportions. And to do that, we use a scale. And our scale can be anything, but in this case I've said that on my picture, if I draw 1 centimeter, that's going to be equal to 1 kilometer in real life. So that's an example of a scale. Okay, and part of this, I said we draw these vectors. Well, another way of calling these vectors are directed line segments. So this is a line with an arrow on it. So that's how we draw a vector. We call them directed line segments. All right, and when we're drawing these pictures, we want to use a method called the tip-to-tail method. And for that, it means that the tip of a vector is the end of the arrow, and the tail is the start of the arrow. So if I draw a little picture over here, this is my tip, and this is my tail. So when we draw vectors, we use what's called the tip-to-tail method. So you can see that now I have the tail of my next vector touching the tip of my previous vector. And that's how we add vectors together, is we use the tip-to-tail method. So when we're adding vectors, we use tip to tail. So second vector's tail on the first vector's tip. And that's how we proceed. Okay. So we're going to do just a couple examples and then we're done with the lesson. So here it says add the two displacements, displacement 1 and displacement 2. So we have 700 meters west and 500 meters west by drawing a vector scale diagram. Okay, now this is actually going to be a bit trickier for me than it is for you because I need to pull out a sort of software ruler so that you can see what that looks like in here. So bear with me. I've got my little ruler here. And first off, I need to set up a scale. So I'm going to say 1 centimeter to 100 meters. So now when I draw 1 centimeter, I'm going to say that represents 700 meters. Great. So I'm going to start over here, and I'm going to put a dot right here, and I'm going to draw a directed line segment 700 meters west. So I'm starting at 10, going over 7, so that's going to take me to 3. And that's my directed line segment. I'll draw a little arrow there. So that's displacement 1. Okay, and now I have 500 meters west again. So I'm going to line that up with the 8. So I'm going 5 over. That's going to take me to 3. So here's my second line. And if you like to use different colors, that might be a good idea as well. I've used the same, but on the next one I'll try to use 2 different colors. So here's my displacement 2. And then the idea here is that we can measure the total length. I can put that at 0. I measure the total length, and well, I haven't done a very good job of my scale diagram, because I should get 7 plus 5 is 12, and you can see that mine ended up being a bit longer than it should be. So hopefully when you do yours, you're a bit more accurate. But here we had 700 meters, here we had 500 meters, so the total displacement is equal to 1200 meters west. And the last thing I haven't drawn on my picture, it's a good idea to draw an indication of your directions. So I've here just said that north is up. In most of your pictures, you'll probably use north as up. Okay, we'll try doing that again. It says, imagine that you are going to visit your friend. Before you get there, you decide to stop at the variety store. If you walk 200 meters north from your home to the store, and then travel 600 meters south to your friend's house, what's your total displacement? Okay, so again, I'm going to take some starting point. I'll draw my north arrow, and I'll say that I'm starting down here. I need to write my scale. So I'm going to say, again, 1 centimeter to 100 meters. And just pick a scale that seems to make sense, seems to work with your numbers. And then I need to actually rotate this. Give me a second to make sure that I know how to do that. Nope. Well, I obviously need to learn this ruler a bit better. So what I'm going to do is, for now, I'm going to switch my north arrow. So I'm going to say here that north is this way. That's fine. You're welcome to do that. So now, I'm going to start at this point. I'm going to go 200 meters north, so 2 centimeters here. That takes me to there. And now I'm going to go 600 meters south, so the other direction. I'm going to line up the 6 with the end. And I'll use a different color. I'm going back down this way, 600 meters. And there we go. Now if I measure the total result, well, I can say this was displacement 1, this was displacement 2. If I measure from the start, I can see that I have 400 meters. So I can say the total displacement equals 400 meters. And that's how we use these vector scale diagrams. So go ahead and try the homework problems at the bottom, and I'll see you in the next lesson.